comes down to how do you convert into radians out of degrees? How do you place things into the correct quadrant? How do we find complementary, supplementary, but this time in terms of radians as opposed to degrees? Remember coterminal angles from last year? Things like that. So we're just going to kind of go through, I don't know, 4 or 5 different things. Then we're going to split up the first section. We're only going to probably get through most of the radian degree stuff. Tomorrow we'll talk about degrees, minutes, and seconds and how those things are going to occur within with this now. It's not going to be as important right off the bat about degrees, minutes, and seconds, but it will become more and more important when we start talking about what are called bearings. Obviously, if you're just going 12 degrees that direction, you could go 12.5 degrees or 12.7 degrees or whatever. And it all deals with minutes and seconds as far as the conversion goes. It's very, very easy to do. So let's look at quadrants and where these come from and how this all works. And what I wanted to throw on there right away was it going straight into radians. Last year when you guys had trig, you guys were introduced to what we call the unit circle. The unit circle obviously went all the way around because it's a circle. And you started at 0 degrees, 90 degrees, 180, 270, and finished up at 360. When you worked with your quadrants, obviously the quadrants start in the top right, quadrant 1, and it goes around counterclockwise. And this in Rocky movies is the only thing that uses Roman numerals anymore. Even the Super Bowl gave up on Roman numerals.
Really?
Yes. Now it's Super Bowl 50. It is surprising. It should just be L. So, one of the things that you will also recall is that obviously quadrant 1 is between 0 and 90. Why does it not include 0, or why does it not include 90? Let me ask this again. What quadrant is that angle in? Neither. It's on a what? Remember the fancy word? It's an axis. What would we call it? What is it? I thought someone just said it. Quadrantal. Remember that?
Oh, yeah.
Oh,
Yeah, now you're getting the heebie-jeebies. So what happens here is that you've got these quadrants, and you also have what are called quadrantals. The quadrantals are when you land on an axis. Okay. The quadrantal occurs at 0, 90, 180, and 270. Well, obviously then 360. When you land on the axis, those are your quadrantals. Obviously, you guys probably remember them as 0, pi over 2, pi, and then 3 pi over 2, 2 pi. That's how those things work. Do you remember the ordered pair when you landed on the quadrantal? Just for fun, see if you remember this. What was the ordered pair there? 1, 0. This one was at 1, 0. What was this one? 0, 1. This was?
negative.
Okay. What is the, let's see here. What is the cosine?
No.
Oh no.
Oh, I got it.
I'm out.
You're done.
What is the
You
cosine
lost me.
at 0? Is it 1 or is it 0? You remember? I mean, obviously, we're not doing this yet. But
Sine is 0, cosine is 1.
correct. As far as the ordered pairs are concerned. So you do a lot of stuff like that. That's where we got your quadrantals, when you had your ordered pairs, when you're on the unit circle. We're not going to get into too much of the unit circle parts today. We'll get to that after break. Yeah. Oh, are you talking about, let's see, that's polar, right? Is that the polar ones?
Well, tau is just 2 pi,
Oh, I totally forgot about that.
so it'd probably be easier if it was just tau over 4, tau over 2.
Is he talking about zero equals
Yeah, because you're saying it would be 0 tau over 4, tau over 2, 3 tau over 4, and then 2, and then tau. I don't. Jeez, I don't even. I honestly. What class did you use tau on something?
Are we in math anymore?
I think Mr. Fontana brought it up last year.
I don't even remember ever. To be honest with you, I don't ever remember using tau. Ever. I now remember what I remember it vaguely, aside from some.
Physics.
Is it physics?
We're going to learn about that next semester.
Okay. I vaguely remember tau, but when it comes down to the math stuff, we keep it within the revolutions of 2 pi because it's easier at this level to think of it in terms of fraction. You're right, tau is a little bit less of the fraction, but you start when you go into the like your standardized tests and stuff like that. We're going back to ACT doesn't use it. You guys won't see it unless you get into some of the physics things and or when you get to the upper level math. That's kind of why they stick with that. That's really cool on top. Isn't that something like that?
Tau is just like a big pi.
Oh, this is, I don't remember my Greek letters. Yeah, tau is the big pi with no curvy legs, right? Or no, I'm sorry, the curvy tilde. It's a flat tilde.
Tilde.
That's tilde. Tilde.
This is
You're probably having nightmares about this. All right. Anyways, let's go back into what you learned about terminal size of vertex. No, it's not so much as geometry. Remember last year when you guys talked about placing an angle on the axis? You had a terminal side and the initial side.
I heard that there's a lot of geometry.
There is. Most of the geometry, when you look at the ACT is written to be for a junior level class. And after your junior year, everybody should have gotten through geometry. So they base a lot of it on geometry.
I heard
Yeah.
Tau is just like a little piece, like half pi. Half pi.
Was I right with the idea? But it had curve inside, didn't it? Like the tails?
Actually, Mr.
Okay, that's right. Oh, okay.
Half pi.
On the ACT, 3 questions are 22 are geometry, 4 are church.
So, what happens here?
Wait, what was the when I get done with this?
When we talk about angles in here, we're going to place them at one spot and then they open up. Obviously, the way that the math is going to work for us is that the first quadrant starts at 0, works its way up to 90. So every angle that we place in space, if you will, is going to have what they call an initial side laying on that axis. And then the angle opens up going counterclockwise, however many degrees. Right? What you're going to be looking at is, can you take an angle, for example, and say, hey, what quadrant will 200 degrees be in? If I try to draw that angle on the axis, like your regular XY axis, when I go to spin that around, Caleb, what quadrant does that wind up in? 3. Now, is it halfway past 3, a little bit past 3? Is it closer to 4?
A little bit faster.
A little bit past 3. So what you would be doing is you'd start here. Remember doing this, drawing around to an arrow? And you'd say that would be 200. Okay? Ooh, what's the reference angle? $1 million. What's the reference angle?
On the other side.
Very good.
I should get extra credit.
I was gonna say.
I'm gonna give you $1 million.
I thought that was too easy.
I was thinking the opposite of that. I was thinking
Write on a piece of paper $1 million.
I was thinking if we had to get it to 270.
Present on the $1 million.
Look at Sydney, she's looking. Did you just say?
Should be like the
You got $1 million
You
bill.
should have drew your
Who's the president on it?
face.
Steve.
Oh.
So,
Really?
so what happens here, guys, is that you have, I'm just asking, we're not talking about representatives yet. I'm just throwing a couple things out there to see if you remember what they are called. We just did all that. Radians. Radians is where the normal world lives. We don't like to deal with degrees. We like to deal with radians because they are rad.
Nope.
Does anyone ever watch Rad?
Oh,
You haven't watched rad yet?
No, not in here.
We'll watch it. We'll watch it tomorrow.
Okay.
We'll watch it tomorrow. So what we have here is what's called a radian. The radian is going to be the unit measure that we're going to use 90% of the time when dealing with trig in trig calc. It's kind of the standard way of using it. When you guys were in geometry, you were introduced and you used degrees because it's a little bit easier to work with and you started going through that. Last year when you were in Algebra 2, you started with degrees, then you shifted everything over into radians. And then you were introduced to that unit circle and you were basically told to do everything without the use of a calculator.
Right.
Right. So radians become pretty easy to use because as we start to use them more and more, they're only built off, well, radians can be converted from any degree measure, but as we get into what you guys remember about that whole unit circle, the unit circle was really only made up of 2 triangles. And the 2 triangles only had 3 different angles. The 2 triangles I'm talking about, if you remember, were your 30, 60, 90s and your 45, 45 90s. Because what happened with those is that you had those special relationships. Hopefully you might remember this. It isn't all in here yet today, but it's kind of, like I said, we're getting towards this. What was the ratio of the sides in the 30, 60, 90? Do you remember that?
Wasn't it
Root 2 and
4?
One of them's 2, was it 2 and?
X 2
2, and then 4, 5? No, it was like
3, 4, 5 is the right triangle, yes. All right, let me ask you this. What triangle, how did we create a 30, 60, 90? Remember how that was created? What kind of a triangle did that come from?
60.
No.
this was 2 years ago. Oh wait,
What kind of triangle is that?
Equilateral.
Equilateral.
half.
So equilateral triangle had all 60-degree angles.
Right.
Yeah.
When you drew the altitude in, it was the perpendicular bisector of the sides. So if this side was 2, this side became a 1 here. Using good old Pythagorean theorem, we got root 3 here. So your side ratios were 1, root 3, and 2.
You guys. Oh, wait, so it was X, 2X, and X.
Yes. In the 45, 45, 90, what did that get, how did that get created?
2, root 2.
No. It got created from a square. Because the diagonal of a square bisects the angles. So you had 1, bless you, and a root 2.
Right.
Well, you guys remember any of that, do you?
No.
Bad time, I got out.
So here's what's happening. When we're going to deal with radians, is that the radian measure, as you go through the quadrants, we start at 0. 180 degrees gets you at pi. To come back around at 360 is 2 pi. Okay. Halfway between 0 and pi is 90 degrees. 90 degrees is half of pi, which is pi over 2. Halfway between pi and 2 pi would be 1.5 pi, but we don't write it like that. We write it as 3 pi over 2. What you're doing here is you're creating and converting degree measures into radian measures. And how you do this is a very short setup. So if you take 90 degrees and you want to convert it into radians, obviously radians is going to be in terms of pi. So no matter what, you're going to have to multiply this by pi.
Oh, over
80, good. So to go from degrees to radians, you take your degree measure, and then you multiply it by pi over 180. Okay. How do you think you go from radians to degrees then?
You do the radian over 180. I don't know.
180 over.
You just flip it, exactly. One. I thought you said 180. I thought you said radian. Yeah, I thought you said radian over 180.
Oh, I meant 180.
It's okay. That's what you said. I'm sorry.
It's
Then they go the other way. You go from radians to degrees. You take the radian value, you multiply it by 180, and you divide it by pi. Okay. That's how that stuff's going to work. A lot of times with radians, most of them will be within, well, it really depends on the problem, but a lot of the conversion stuff today, I think most of it stays within one revolution. What I mean by that, by one revolution, is one time around, between 0 and 2 pi. Obviously, as we get going, you can have other values, you can have other things. If you guys recall last year when you graphed sine, cosines, and tangents, you had cycles where you'd have your period, it had some certain periodicity to it, where it would take so long to repeat itself. It's the same idea. I mean, you'll always wind up at the same spot if you turn around again. So every time, if you're facing forward, if you turn around 360 degrees, you're facing forward again. Turn around and facing forward. Correct. Two wrongs don't make a right, but 3 lefts do. Sure. Stand up.
I feel like I did this last year.
You probably did. That's what makes it funny. Turn left. Turn left. Turn left. Which way you're facing?
But I started this way.
So you turn.
3/4 of the way around.
Facing
So she turned right.
So you turn right.
Why go 3/4 when you can go 1/4?
Yeah, but that's dumb.
What if they're all one-way streets? What if you need to make a right, but every street is you can only turn left?
You make 3
And
lefts.
you go
Correct,
back.
then you'll be where you need to go.
Yeah, I had to do that one time because my clicker was out.
Were you on the phone too?
No, it was just late. Did you do lefts, really?
No.
Co-terminal.
Never happened? Yeah, when I multiple and then I had 3 lefts, really? No, remember, if we learned hand signals? You just walked through it, little. I had to.
Let's try this thing.
I understand.
All right, now let's do
No,
this.
I
Stand
get
up.
it.
I will go with you. All right, ready? All right. I want you to turn right, and I'm going to make 3 lefts, and let's see which way we go. Both go. Ready? Go.
Yes, I
Nice.
understand
Oh.
that it makes
Well, she just
like,
turned right.
3 lefts makes a right, but it doesn't make like never.
What if you make 3 rights? What would you be going?
Left would go left.
But you have to also.
Because it doesn't make sense how it all works out. You know what? Just
Have you ever played Pac-Man?
Oh, I love Pac-Man.
yeah, I have actually.
Okay. So with Pac-Man, oh, here we go.
It's a triangle. You should just draw it.
That'd be too easy.
That's
very
very
good. There you go.
Now, color that.
Give it an eyeball.
So when you're Pac-Man
Uh-huh.
and you need to turn left,
I'm next to
but oh no, you got the ghosts coming after
Yeah,
you.
you gotta watch out for Clyde.
You're gonna turn right. You're gonna turn right again. Turn right. Oh, whew, I escaped the ghost.
Thank you.
I said I understood.
Watch out for Clyde.
Anyway,
He's gonna get
Were you recording that?
Yeah, it's not fair.
co-terminal. You guys remember what co-terminal meant?
No.
No? Sweet. I kind of figured that was going to happen. So if I want to talk about what's called co-terminal. Co shares.
Yes.
Oh, I know what it is.
Terminal. It's that it's that side. Co-terminal angles share the same terminal side. Okay? Co-terminal angles share the same terminal side. For example, if I put this angle here and I call that pi over 4. Oops. If I should call that pi over 4. Do you guys remember what pi over 4 was in degrees?
45 degrees.
Good. Pi over 4 is 45 degrees. Everybody okay with that? Now, a co-terminal angle with pi over 4 would be I still start at the same initial side, and I loop around, and I wind up here again.
So, 60 plus 45?
Yeah, it'd be 360 plus 45, which would be at what? 405. So co-terminal angles, 45 degrees and 405 would be co-terminal. There are two angles that share the same terminal side. In terms of radians, it was pi over 4. And then if I add 2 pi to that, remember, a lot of times when we're doing these things, when we're adding pi, we're going to do some quick conversions to make fractions that make sense. So if I have pi over 4, and I'm going to add 2 pi, in order to have a common denominator, what would I turn that into? 8 pi over 4, right? So I'd add pi over 4 with 8 pi over 4, and I would get 9 pi over 4. These two would be coterminal, right? We did a lot of that. Now you could have positive coterminal and negative coterminal. Positive and negative angles just mean the different direction that you're starting. When you have a positive angle, positive angles, oops, let me put this on this one. Can I go to a clean one? I need to get ahead of myself here.
Wait, where? Oh, you added it. Never mind, never mind.
Wait, is that
Positive angles go counterclockwise. Negative angles go clockwise. Okay? That's the difference between the two. Each one of them starts always on the initial side. They always start on the initial side, and then they just rotate around. Okay? usually what you're gonna be asked to do is find one positive and one negative coterminal angle, which basically means you're gonna add 360 to an angle or subtract 360 to an angle. If you're in radians, you'd add 2 pi or you would subtract 2 pi. Pretty sure most of you guys hopefully remember that from last year. Well, I know, it's like a bad nightmare, but it comes back. Yes, sir?
So if you go to the negative, would it be negative 9? Like say you land on
If I start here, give me an angle.
yeah.
What angle do you want to say?
So if you're going clockwise, you land in that first, I guess, well, would be first quadrant.
Yeah.
But it would be a fourth one.
No, it's still first quadrant.
Okay.
It's still, the quadrants don't change with positive and negative. They're still that.
Okay.
Those will never
I
change.
mean, would you be going 90 or would it be 270?
If it says negative 90, if I'm going to go negative 90 degrees, how I would mark that is I would draw it like this. That's negative 90 degrees.
But a positive.
But if I would say 270, I would draw it like this. That's what that would look like. Does that make sense? It just tells you the direction that you're going. Okay. What else is there? Yeah. The very basics, very, very simple basics to go. You have to remember how to work with radians and stuff. What was complementary versus supplementary? Do you guys remember that? What comes first in the alphabet? Complementary or supplementary? Which one comes first in the number line? 90 or 180? It's another way to remember that. Complementary are your two angles that add to equal 90. Two angles add to equal 180. Or in terms of radians, two angles that are complementary add up to equal what? Pi over 2. And then this one would be, this would probably be the only new thing that you might see today, is how do you get a complementary angle of pi over 6? Sure, why not? What's complementary to pi over 6? I don't know. But what does it have to add up to equal? It has to equal plus something. It has to equal pi over 2. So in my head, I know I'm adding fractions. When I'm adding fractions, I have to have the same denominator. So how can I rewrite pi over 2 in terms of a denominator of 6? Isn't 3/6 the same thing as 1/2? Okay. Pi over 6 plus what is 3 pi over 6? But 2 pi over 6 is pi over 3.
So is pi over 7?
It's things like that that'll be the new thing. And then obviously if you had to add to equal pi, you would just work with the other way. And when you're adding to pi, that's really, really easy. Because pi over 6 plus what over 6 equals 6 pi over 6. What I'd like you guys to do today the video? Yeah, I put it on 1 second. Yeah.
You give me credit.
No, I forgot to do that. I should do that. I need to cite my source. I will do that.
That's illegal. Putting that on there.
So, tell me what happened.
Let's do this.
I'm dead. 7 through 6. Oh my goodness.
And what's our work tomorrow?
If you had a test tomorrow, it's 34.
We're gonna do probably the same section, but I'm gonna add in the, what do you call it? Degrees, minutes, and seconds, as well as a couple of the central angle style problems.
Alright, look at how good that F is.
Linear speed, things like that, so.
Really?
It's an area of the sector. You did most of it last year, just some. Watch the video, you'll be all right. Okay?